So in this video, we shall continue our discussion of the vector cross product and see some computational aspects of this particular product that we have learned. So the first thing to note is that we are interested in calculation of torque, which is a vector, and which is due to the product or the operation of two vectors, which is force and the position vector. So now, if we do have a coordinate system, inertial coordinate system, and in that coordinate system, if we know the force vector and the position vector gives the location where the force is applied, then we can calculate torque in that coordinate system if we know how to calculate the cross product. It's pretty much the same for the angular momentum, which by definition is the same position vector that we've been talking about. This is a position vector of the particle. I'm sorry. So there's a slight difference here. This is a position vector of the particle. This is the position vector at the point at which the force is applied. And but the you can see that it looks very similar. Momentum. Okay. Now momentum is mass into velocity. Just a quick reminder. No doubt that it's a vector. So here we go again, two vectors combine to give another vector due to the vector cross product, and we get the angular momentum of the particle, and this is the torque due to a force. Now let's look at the actual computation of the cross product. So once again I repeat, you can get the force, you can get the position vector very easily. Pretty much the same thing for momentum. And in particular, I want to emphasize that you're going to get the force in a component form. For example, on the xy plane, it will be something like 10I plus 2j can be an example of a force vector in the xy plane. And position vector also in the xy plane can be given in the form of 2i plus 5j or something like that. Mind you, what I'm trying to tell you is that the vectors are given to you after being resolved in I and j axis. Same story for momentum and position vector, let's say on the plane, for a particle moving on the plane. Now, given that the vectors are given in a resolved form, how does one carry out the computation? Right. The two key properties of the cross product, which we looked at last time, are the ones which are going to play a role in getting us the formulae that we are seeking. So this is the key thing. The vector product is not commutative, but on the other hand, you just have to put a minus sign if you want to reverse the order of the vectors. The second one, which I said, does have a graphical proof which I can post for you. It's very graphical, just like the ones that we've seen before. And this is the so-called distributive law, and it's of the form that you can guess, and this can be proved. With this, we are done. These are the only two things that we need to know. Now, for a couple of simple observations, let me just go back to the dot product once and remind you that we needed to know such kind of combinations. This is mod I dot mod I cos 0, because the angle between I and I is 0, and this is 1 into 1 into 1 is equal to 1. Similarly, I dot j is going to be mod I dot mod j cos of 90. Not a nice thing to write 90, pi by 2, and this is again 1 into 0 is equal to 0. So you could do this for I dot k, j dot j, and so on, but you get the idea that these unit vector products are fairly easy to evaluate. And we use this actually to derive the formula that a dot b is actually equal to ax bx plus ay by. Now these are all scalars. Now we need to know the cross product of the unit vectors. So this is going to help us cross product of the unit vectors. So let's start I cross j. Now let's visualize I cross j. This is the x-axis, this is the y-axis, and this is I, this is j. Mind you, the magnitude is 1. And what is k? K can be thought of as this something coming out of the plane of the paper, z-axis, and k is in this direction. Okay, out of the plane of the paper at this point of the origin, I think we are representing it like this, and into the plane of the paper. This is worth repeating all the time. We're going to use it a lot. Right. So now I dot j has a magnitude of, I think I should just once again repeat. If when you do A cross B, the magnitude is mod A, mod B, and this is the thing that we realized last time. The you should represent mod of A cross B like this, and it's better to give a positive quantity, and so I'll put mod here again, sine theta, where theta is the angle between A and B. Now we know how to find out the direction. It's by the so-called right hand rule. So I won't repeat this. I think what I want you to be convinced about is that it's 1 into 1 into sine pi by 2, which is also 1. What is 1? The magnitude of I cross B, I cross j. And I want you to figure out the right hand rule on your own and convince yourself that I cross j is actually in the direction of the z-axis, and therefore and of magnitude 1, so it's equal to k. And similarly j cross k, just go ahead and convince yourself that it is equal to I, and k cross I is equal to j. Now if you are going to convince yourself, then you can also quickly realize that j cross I will then be minus k, simply because of what we said about I cross j being equal to minus of j cross I, and similarly k cross j is equal to minus I, and I cross k, I'm just looking at the left hand side, is equal to minus j. Now all of this can be easily memorized in the form of a mnemonic, and that's what I'm going to write on the next page. And this mnemonic I use all the time, and probably everybody uses this mnemonic all the time. So you draw a circle and just write I, J, K. So if you are going, if it is I cross J, you get to K. If it is J cross K, you get to I. And if it is K cross I, you get to J. But if you're going in the anti-clockwise direction, so somebody says, what is K cross I? Then you are going in the clockwise direction. But if somebody says, what is, so therefore you will write this as equal to J. But if somebody says, what is K cross J? Now you're going from K to J in the anti-clockwise direction, and therefore this is equal to minus I. So using a quick diagram like this, one figures out the cross product between the unit vectors very easily. And that is all you need to know, because now is the time that these two formulae, that is A cross B plus C, is going to come into play. So this is equal to A cross B plus A cross C. Now this is all you need now to get your formula for two random vectors. And what I mean by two random vectors is, let's stick, okay, let's not kill ourselves with 3 dimensions, because mind you, our problems in this chapter are going to be 2D. The exact importance of 2D I'll tell you. Basically what I mean by 2D is all the forces that are going to be encountered are going to be in the plane. Okay, so it'll only be of the form something into I. So I'll write it as fx into I plus fy into j. So the forces will always be of this form. Just to remind you, these are scalars. And similarly, the position vector. So let's say that the force is applied here. Then the position vector of this particular force is going to be r, which is also going to be something like xi plus yj. And what is x and what is y? I think you know. So for example, this is going to be x and this is going to be y. So they're always going to be of the form something I cross something j. So I hope that this is not sounding too abstract. I'll take a vector which has got only the I component and the j component, and take another vector which has got only the x component and the y component. Okay, and I'm going to ask the question, what is A cross B? So please note that in the actual physics, so this could be, for example, the position vector, this could be force, or this could be the position vector and this could be the angular momentum. So let's write it R and F. These are the important cases in physics for us, R and L. Oh, what a bad mistake. P. I'm sorry. R and P. Okay, and we're trying to calculate torque and angular momentum. Now, the just once again, please note what we already have is an origin, and we have the coordinate system. And the correct question to ask is, what is the angular momentum? Okay, what is the angular momentum and what is the torque with respect to this coordinate system, right? So the position vector is drawn from this origin, right? Just want to tell you that these two will depend upon what is your coordinate system. Okay, and the other thing that I told you before, I want to reiterate that when you're doing a problem, you do this calculation, but stick to the same coordinate system, right? So we're all set. We got what you want. Once the coordinate system is fixed, once the origin is fixed, you know what is A, you know what is B, and you're ready to go. So the question is, what is A cross B? This is equal to AXI plus AYJ cross bxi plus byj, and once again the same thing that we did last time. We want to use the distributive property, so let's call this as b. Let's call this vector as c. Mind you, this is a vector, and let's call the whole vector as a, so that we know what we mean by the distributive property. So this is the same as a cross b, and a is also a vector. The whole thing is just calling it a plus a cross c, because the distributive property holds. And what this actually means is, this is axi plus ayj cross bxi plus axi plus ayj cross byj. Now, because so I could use the same idea again. Let me just change. Now this is interesting, and it's not an overkill at all. I'm going to change to bxi, but I'll put a minus sign, cross axi plus ayj, minus sign again, byj cross axi plus ayj. Just want to tell you that you know that each step is very easy, and in principle the computation can be done, but at the end of the day perhaps we want to remember the end result as a formula, but we'll worry about that later. Let's get to the formula. Why I'm saying it's easy is because we can use the distributive property all over again here and here, and we'll end up with I cross I cross j, j cross I, j cross j, which are easy. So let me just transfer this to the next page. I sort of remember what's happening. bxi cross with axi plus ayj minus byj cross axi plus ayj. Now, quick reminder, I think I missed out on something. I cross I is 0, and why is that? I think that's pretty easy. Mod 1 into, sorry, mod I into mod j, I again, into sine of 0, and that is 0. Okay, so all we need to worry about is I cross j, and I think I cross j is k, so it is minus bx ay k, because I cross j is k. Then we have j cross I is minus k, and therefore this will be plus ax by k, and then j cross j, you can forget about it. J cross j is 0. And finally we have this wonderful answer that look at how easy it is to remember this. And what is this? I'll tell you in a minute. This is what is the answer for two vectors which are in the xy plane. So once again I repeat, this is the answer for what? This is A cross B, where A is AXI plus AYJ and B is BXI plus BYJ, and what you see here is that the direction, the answer is a vector whose direction is in the direction of k, and whose magnitude, perhaps because of its whatever in perhaps because of its there is some symmetry here. It's not so difficult to remember, so you got to remember it as ax by minus bx ay into the direction is k. So the direction is absolutely no doubt. Now, how does one remember this? I don't know. Right now I couldn't remember it by brute force, ax by minus bx ay. Right? So this is the answer. And now there is a way to remember the formula very neatly, even for vectors which are 3D. I shall not write it now, but there is a way to remember this. Right now we'll just remember it in 2D. So finally, one more time, if A is a vector in the xy plane, and if B is a vector in the xy plane, then A cross B magnitude is equal to axby minus aybx, and the direction is in z-axis direction. Okay, it could be, if this quantity is positive, then positive z-axis. If this quantity is negative, then it will be in the opposite direction, right? So so finally we write it as A cross, I think I made a mistake here. I'm sorry, I think I'm making a lot of mistakes. I'm sorry about this. This should be also then the length is always positive. So if I'm asking for mod of this vector, then length, and the direction is either in the z-axis or in the negative z-axis. Okay, so finally we just write it as A cross B is equal to axby minus aybx times k. So once again I repeat, if this quantity is positive, then it's in positive z-axis direction. If this quantity is negative, then it's the opposite direction. And we're done. If it is B cross A, then we just put a negative sign to this. So the computations are fairly easy. Now what we need to look at is in the next class. Now we'll follow K and K very carefully, and we'll try to calculate torque, which is precisely what calculation we just did, but we'll do it carefully from Kleppner's book, the examples. So you can see that this is going to be a 2D vector, this is going to be a 2D vector. We're going to be able to calculate torque very easily. All you need to do is fix the coordinate system. So before you, I think this is worth repeating at this time. Somebody says, what is torque? The first thing you ask him is, please can you tell me what's your inertial coordinate system? Okay, right? And next thing you need to ask is, what is the angular momentum? And now this is going to be r cross p, and once you get the coordinate system, you can do this computation. And I repeat, we are looking at examples where this is in the xy plane and this is also in the xy plane. So please don't worry about the general case. Let's worry about the things that we are immediately in our syllabus for 11th and 12th. So once again, this is in the xy plane, this is in the xy plane, and it's always going to be the case. And therefore you just need to remember this formula and nothing else. So we'll make these computations of torque and angular momentum for a particle to start with, and then for a system of particles. And let me tell you upfront that, okay, maybe it's worth repeating here itself. Now, because of the nature of the problem that we are doing, and therefore one of the computations is going to be very simple. Okay, in general this is difficult, but what you just realized, we just realized that the answer is going to be something times k. Now that's very good news. And this answer is also going to be something times k throughout our chapter. So what's happening in this chapter, as you will notice, is that they often call this as tau z. Okay, this quantity, because it's in the direction of the z-axis. And mind you, I'm not putting an arrow because it's a number, and this is called Lz. So this is a confusing part, because we are doing a specific 2D problem. The torque as a vector will always be in the direction of k direction. The angular momentum as a vector will always be in the direction of k, and often we are interested only in the Lz component of the angular momentum, which is the Lz, and this is tau z. Right, so often we'll be referring to tau z and Lz as scalars, and you should not get confused, because actually you're right, torque and angular momentum are vectors. And we know the formula for tau z and Lz. So what is going to happen here is we're going to calculate tau and L for a particle. That's going to be the next video. And also then for a system of particles, where we just add up the tau for each particle, we add up the angular momentum for each particle. But here is the good news. Now, because we are interested in tau z and Lz, though these are vectors, we'll end up adding them like numbers, because we're only interested in tau z and Lz, and therefore the whole calculation is going to be very easy. But let's actually do it, and there are lots of examples which will make sure that you are able to realize how easy it is. So let's get to the concrete examples now. I've told you beforehand that there are a lot of good things in this computation, and we'll find it fairly easy.